Welcome to the Explainer. Today, we're going to do something really cool. We are taking a deep dive, a technical tour of how one of the world's most powerful open-weight AI models was actually built, piece by piece.
So, late in 2025, the AI world was absolutely stunned. Out of nowhere, this open-weight model, DeepSeek V3.2, shows up, and its performance is right up there with the industry's best proprietary models. Think GPT-5 and Gemini 3.0 Pro. This was huge, and it left everyone asking one big question. How on earth did they do it?
So here's how we're going to break it down. We're going to follow their journey step by step to see how the team tackled these huge AI challenges one at a time. Okay, let's jump right in. All right, first things first, let's just set the stage here so we're all on the same page about why this breakthrough is such a massive deal. So how can an open-weight model go toe-to-toe with the closed-source giants? Well, the answer isn't some single magic bullet. It's actually a series of really brilliant, small improvements that all build on each other. So let's see how this whole thing came together, starting right from the very beginning with the foundation. Okay, so the very first problem you face when you're building a massive AI model is all about efficiency. I mean, think about it. How do you build something incredibly powerful without it just collapsing under its own weight? Or in this case, its own memory requirements. So the whole story kicks off in late 2024. That's when we see DeepSeek V3 and its partner, R1, which was really focused on reasoning. And from there, you can see it was just one key release after another over the next year. Right out of the gate, DeepSeek's first big innovation was something they called Multi-Head Latent Attention, or MLA for short. The easiest way to think about it is like a super smart compression technique. Its whole job is to save a ton of memory when the model is actually running. And this image, wow, it just illustrates the idea perfectly. Instead of storing these absolutely massive key and value tensors, MLA squishes them down into a much smaller latent space. This dramatically cuts down on how much memory you need in what's called the KV cache. So yeah, it makes running the model way more efficient, even though it does add one tiny extra calculation step. A worthy trade-off for sure. Okay, so they've got efficiency handled. What's the next boss level? Well, it's reasoning. This is the big one. How do you actually teach a model to think, step by step and solve really complex problems without making mistakes all the time? This is where the DeepSeek R1 model brought in a new technique called reinforcement learning with verifiable rewards, or RLVR. This is clever. Instead of just relying on humans to say, good job, the AI learns by getting rewards for answers that a computer program can prove are 100% correct. And what I love about this is just how simple and powerful it is. Look at this example. The AI tries to solve a math problem. The output gets checked against a simple calculator. If the answer is 35, boom, the model gets a super clear, verifiable, you got it right signal. This reinforces that specific path of reasoning, making it stronger for next time. All right, so the next hurdle, as these models start processing longer and longer texts, you run into a huge problem. The standard attention mechanism, how the model decides which words are important, it becomes this massive computational bottleneck. It just grinds to a halt. DeepSeek knew they needed a much smarter, much faster way for the model to pay attention. And their solution was pretty elegant: DeepSeek Sparse Attention, or DSA. Think of it like this. Instead of forcing the model to read every single word that came before, it learns how to skim, just like a human would. It learns to pick out and focus only on the really important words. Now, to really get why this is such a big deal, you gotta look at how it's usually done. On the left, you've got regular attention. It looks at every single previous word. It's thorough, for sure, but man is it slow. Then you have something called sliding window attention. On the right, it's faster because it only looks at a small, recent window of words, but the risk is huge. It can easily miss important context from way earlier in the text. This is where DSA comes in as the best of both worlds. It's not a fixed window. Instead, the model learns a unique, sparse pattern of attention for every single token it processes. This is a game changer. You get a massive improvement in efficiency, but you're not stuck with that limited, fixed window. This flowchart breaks down exactly how it works. You've got this lightning indexer that quickly scores all the past words for how relevant they are. Then, a selector just picks the top few highest scoring words. That's it. It creates this sparse mask for the final attention calculation. It's a brilliant two-step system that intelligently trims down the context, and for the nerds out there, this is what takes the computational complexity from quadratic all the way down to linear. Huge.
Okay, we're almost there. The final piece of this whole reasoning puzzle was a big one. It wasn't just about getting the AI to solve problems. It was about teaching it to recognize and, even better, fix its own mistakes.
And the DeepSeek team put their finger on a really critical flaw in how a lot of models are trained. They said correct answers don't guarantee correct reasoning. A model can just get lucky and stumble into the right answer using totally flawed logic. This realization is what led them to develop a new method for the AI to basically check its own homework. And that led them to this concept of self-verification and self-refinement. What does that mean? Well, it's pretty wild. They essentially trained one AI to act as a strict judge of another AI's step-by-step reasoning. This diagram just lays it out so clearly. You have one model, LLM1, that tries to write a mathematical proof. But then a second model, LLM2, comes in acting as the judge. It reviews the proof, spots a fatal flaw, a really bad math error, and slaps it with a score of 0. But crucially, it doesn't just fail it. It provides specific, targeted feedback on why it failed. And so, finally, with all these incredible building blocks in place, the efficiency, the reasoning, the self-correction, the team was ready to put it all together. They were ready to assemble their masterpiece, DeepSeek V3.2. And here it is. This is really the aha moment. This is the final architecture of DeepSeek V3.2, and it brings together everything we've been talking about. You can see right there, inside the attention block, how those two brilliant, efficient attention mechanisms, MLA and DSA, are now fused right into the core of the model's design. It's the whole package. So when you boil it all down, what's the big takeaway? The crucial point is that DeepSeek V3.2's incredible success isn't because of one single silver bullet. No way. It's about the powerful synergy of all these innovations working together. You've got the memory-saving MLA, the super-fast DSA, the better reasoning from RLVR, and that internal scrutiny from self-verification, all of it combined into one powerful, efficient, open-weight model. That's why this matters. You know, the release of models like DeepSeek V3.2 really marks a major shift in the entire AI landscape. For the first time, truly state-of-the-art AI capabilities are open and accessible to everyone, not just locked away in a few big tech companies. And that leaves us with a very, very exciting question to think about. What happens next?